In mathematics, we frequently need to describe collections of objects that are of interest to us. We gather these objects together in what's called a set. For us, a set is nothing more than some unordered collection of interesting objects. So for example, if I wanted to tell you about the vegetables that I grew in my garden this summer, I might write them down as a list. I grew tomatoes, cucumbers, and peppers. In order to indicate that it's a set now of interesting objects, I would enclose them in a curly brace. One of the features of that notation is to emphasize that the order that I wrote them down in really doesn't matter. It's just a collection of the vegetables that I grew, and they're written down in no particular order. For us, we're typically going to be talking about sets of numbers. So there's some commonly occurring sets that have traditional names, and we should review those that terminology. So for example, you may be familiar with the natural numbers. The natural numbers include 0 and the counting numbers 1, 2, 3, etc. Notice I could never list them all, so I've indicated that with an ellipsis, this ... here, which tells me just to continue the pattern on forever. I've enclosed them in a curly brace to indicate that it's the set of natural numbers. The order that I wrote them down in is somewhat natural in that I've written them in increasing order, but that wasn't necessary to describe the set. There are also the integers. That includes the natural numbers, but it also includes each natural number's opposite value. In other words, -1, -2, -3, etc. So I include all the natural numbers and all the opposite values, and together that forms a set called the set of integers. I can be more constructive. We can form what are called the rational numbers. Rational numbers are ratios of polynomials. I have to be more descriptive in the way that I write this down here. I'm going to say it's the set of numbers that look like P over Q, where P and Q are integers. So I'm going to say such that P and Q are integers and Q is non-zero. I don't want to divide by 0 here. That results in an undefined expression, and so I have to add that condition to this description of this set. Rational numbers includes numbers like 2 over 3 because 2 is an integer, 3 is a non-zero integer, and the ratio is therefore a rational number. It also includes integers themselves, like -5, because I can write -5 as a fraction, -5 over 1, for instance, or I could even write it as -10 over 2. It's not important that there's different ways to write it as a ratio. What's important is that there's at least one way, and that's what makes it a rational number. 0 is also a rational number. I can write it as 0 over 1. More generally, we're interested in the real numbers. The real numbers are a little bit more delicate to describe as a set, but for our purposes, we'll just think of it as all the values on the real number line. So you should think of this as contiguous line of numbers, and it includes all the numbers that we discussed above, but also a lot more. So for example, it includes integers like 0 and 1. It includes numbers in between, like rational numbers like 1/2. It includes negative numbers like -5. But it also includes lots of other values that are not rational. And those are called the irrational numbers. So irrational numbers are real numbers which are not rational. In other words, it's not possible to express it as a ratio of integers. Classical examples of those would be like the number square root of 2. What is square root of 2? It's the positive real number, which I square to get 2. So in other words, square root of 2 is the number that when I square it gives me exactly 2. It turns out that square root of 2 cannot be expressed as a fraction. That's a non-trivial fact, but it is true. I can ask a calculator to estimate its value for me, and it tells me that the value is approximately 1.414. So if I was to square 1.414, I would get approximately 2. And we can see that it's on the real number line, a little bit to the right of 1. Other famous irrational numbers is the constant pi. What is pi? Take a circle, look at its diameter. and form the ratio of the circumference, that is the distance around the circle, and divide it by that diameter, that length through the center. And that ratio will always be the same regardless of how big your circle was, and that constant value is what we call pi. Of course, pi is approximately 3.14, but it is not a rational number. It cannot be expressed as a ratio of integers. It's some point on the real number line that fits somewhere in between all the rational numbers and all the whole numbers. A little bit to the right here, close to 3. The story does not end with irrational numbers. There are other numbers that are non-real. So for example, the symbol square root of -2 is not a real number. Why is that? Well, I can't square any real number and get -2. So in other words, if I look for a number whose square is -2, let's call it x, whenever I square a real number, I'm going to end up with a non-negative result. So this equation here has no solution, and therefore square root of -2 is not a real number. You may be familiar with imaginary numbers in the complex number system as well, and that extends the real numbers beyond the real number line in order to give a meaning to symbols like square root of -2.